Hello my dear students, welcome to my YouTube channel, that's Concepts of Chemistry. Before starting today's lecture, please do subscribe my channel. My dear students, today's topic for the lecture is sp3d2 hybridization with two lone pairs in the main structure. And for this concept, I'm taking the example of xenon tetrafluoride. So our today's example is xenon tetrafluoride, that's xeF4. Now, before starting the hybridization, let's make the Lewis structure of xenon tetrafluoride. So that's my xenon, the first fluorine over here, second fluorine over here, third fluorine over here, and the fourth fluorine over here. Now let's talk about the xenon atom. Xenon, as we all know, xenon is the member of group number 18, that's noble gases, which signifies that xenon is going to have 8 electrons in its valence shell. So I'm going to mark 8 electrons around xenon in the Lewis structure. So see the Lewis structure, that's the first electron, second electron, third electron, fourth electron, fifth electron, sixth electron, seventh electron, and the eighth electron. Now let's talk about the fluorine. What's the atomic number of fluorine? That's 9. So its configuration will be 2, 7. That means fluorine is going to have 7 electrons in its valence shell. So let's mark 7 electrons around all the fluorine atoms. So I'm marking the electrons for the first fluorine. That's the first electron, second electron, third electron, fourth electron, fifth electron, sixth electron, and the seventh electron. Now let's come to the second fluorine. That's the first electron, second electron, third electron, fourth electron, fifth electron, sixth electron, and the seventh electron. Now let's come to the third fluorine. That's the first electron, second, third, fourth, fifth, sixth, and the seventh. Now let's come to the fourth fluorine. That's the first electron, second, third, fourth, fifth, sixth, and the seventh. Now what's gonna happen? All the fluorine atoms will make 1-1 bond with xenon. So that's the first bond of first fluorine, that's the second bond of second fluorine, that's the third bond of third fluorine, and that's the fourth bond of fourth fluorine. Now let's count the number of valence electrons for all the fluorine after the formation of 1-1 bond with xenon. So I'm counting the number of valence electrons for the first fluorine after the formation of 1 bond with xenon. So that's the first electron, second, third, fourth, fifth, sixth, seventh, and the eighth. So that means first fluorine has attained octet, that is 8 electrons in its valence shell after the formation of 1 bond with xenon. Now let's count the number of valence electrons for the second fluorine after the formation of 1 bond with xenon. So that's the first electron, second, third, fourth, fifth, sixth, seventh, and the eighth. So the second fluorine has also attained octet, that is 8 electrons after the formation of 1 bond with xenon. Now let's count the number of valence electrons for the third fluorine. So that's the first electron, second, third, fourth, fifth, sixth, seventh, and the eighth. So that means third fluorine has also attained octet, that is 8 electrons after the formation of 1 bond with xenon. Now let's count the number of valence electron for the fourth fluorine. So that's the first electron, second, third, fourth, fifth, sixth, seventh, and the 8th. So the 4th fluorine has also attained octet, that is 8 electrons after the formation of one bond with xenon. So that means all the fluorine atom has attained octet after the formation of one bond with xenon atom. Now let's count the number of valence electron of xenon after the formation of 4 bonds with 4 fluorine atoms. So that's the first electron, second, third, fourth, fifth, sixth, seventh, eighth, ninth, 10th, 11th and the 12th. So that means xenon has attained 12 electrons in its valence shell after the formation of 4 bonds with 4 fluorine atoms. So this is the case of expansion of octet. Why xenon is able to expand its octet? Because xenon is having vacant d orbitals, or we can see vacant orbitals in d subshell. That's why xenon is able to expand its octet, that is to have more than 8 electron in its valence shell. Now let's talk about the reason. For the reason about this thing, let's start the hybridization process. Now xenon, as we all know, xenon is the member of group number 18. The group number 18 of periodic table is helium, neon, argon, krypton, xenon, radon and the oganesson. Now helium is from period number 1, then 2, 3, 4, 5, 6, 7. Now from here it is clear that xenon belongs to the period number 5. Now what's the general electronic configuration of group number 18? That's ns2 np6. So the electronic configuration for xenon comes out to be 5s2 5p6. So we got the electronic configuration, the valence shell electronic configuration for xenon to be 5s2 5p6. Now xenon electronic configuration is 5s2 5p6. Now xenon is also having 5d subshell with 0 electrons in it. That means vacant d subshell, or we can say vacant d orbitals. So now let's make the orbital diagram in the form of boxes for these subshells and the orbitals. So as we all know, the s subshell has only one orbital, so that's the 5s, and I have taken orbital in the form of boxes. Now let's talk about the p subshell. In p subshell we know that there are total 3 degenerate orbitals. What are the degenerate orbitals? The orbitals that have equal energies. That stands for degenerate orbitals. And in 5p subshell, or we can say in p subshell, we always have total of 3 degenerate orbitals. Now let's come to the 5d. In 5d, we are having in total of 5 degenerate orbitals. So these are the 5 degenerate orbitals of the d subshell of 5th shell, that is 5d. Now let's fill the electrons according to the electronic configuration in these orbitals. The 5s is having 2 electrons. So I'm going to fill 2 electrons in the first box of s subshell, that is in the orbital of s subshell. So that's the first electron with the spin of +1/2 and the second electron with the spin of -1/2. Now let's fill the electrons in 5p subshell. We have to fill the 6 electrons over there. So in 5p subshell, we are having 3 degenerate orbitals. So we are going to fill 6 electrons according to the Hund's rule. And Hund's rule states that in case of degenerate orbitals, firstly, all the orbitals will get 1 electron each with a spin of +1/2. After that, pairing will start. So let's fill the 6 electron. So that's the first electron with a spin of +1/2, second electron with a spin of +1/2, third electron with a spin of +1/2. So now firstly, all degenerate orbitals have got 1 electron each. So now pairing will start from the 4th electron. So that's the fourth electron with a spin of minus 1 by 2, fifth electron with a spin of minus 1 by 2, and the sixth electron with a spin of minus 1 by 2. And that's our ground state. Now, let's come to the Lewis structure. In Lewis structure, you can easily see that xenon atom is forming total of 4 covalent bonds. 4 covalent bonds. Now, all the bonds between xenon and fluorine are the single bonds. That means all the 4 covalent bonds are 4 sigma bonds. That means if xenon has to form 4 sigma bonds, then xenon atom must have 4 atomic orbitals containing 1 electron each, so that 4 orbitals of xenon can overlap with the atomic orbitals of 4 fluorine atoms for the formation of 4 sigma bonds. So let's come to the electronic configuration. I'm repeating it again. In the Lewis structure, we found that xenon atom is forming 4 sigma bonds, and for the formation of 4 sigma bonds, xenon atom must have 4 atomic orbitals containing 1 electron each, which can overlap with the atomic orbitals of 4 fluorine atoms containing 1 electron for the formation of 4 sigma bonds. For that thing, what we are gonna do? Here, in this case, there will be the excitation, or we can say promotion of electron from 5p orbitals to the 5d orbitals. So that's the first electron which is going to excited or promoted from 5p to 5d. Now, this is the second electron which is going to be promoted or excited from 5p to 5d. So we have jumped or promoted 2 electrons to achieve 4 unpaired electrons in 4 different atomic orbitals for xenon atom for the formation of 4 sigma bonds. So let's make the excited state now. That's the 5s. These are the 3 degenerate orbitals of 5p. These are the 5 degenerate orbitals of 5d. So in 5p we got the 3 degenerate orbitals, and in 5d we got the 5 degenerate orbitals. So now let's fill the electrons after the excitation. The 5s is having 2 electrons. The 5p is now having total of 4 electrons, because 2 of the electrons from 5p has excited to 5d orbitals. So we got the 2 electrons in 5d. So that's our excited state. Now, from this point, intermixing of atomic orbital will start, and those atomic orbitals will intermix which are having 2 electrons, and the orbitals which are having 1 electrons, and only those orbitals will intermix which can form only sigma bonds but not the pi bonds. I'm repeating it again. In hybridization process, intermixing of those atomic orbitals will take place which are having 2 electrons or which are having 1 electrons, and the atomic orbitals which are having 1 electron must form only the sigma bonds but not the pi bonds. So here we are having 1 orbital in S subshell which is having 2 electrons, 1 orbital in 5p which is having 2 electrons, 2 orbitals in 5p and 2 orbitals in 5d which are having 1 electrons. So there will be the formation of 4 sigma bonds. So from this step, intermixing of atomic orbitals will start. 1 orbital from S, 3 from the p and 2 from the d will intermix with each other. I am writing 1 s orbital, 3 p orbitals and 2 d orbitals will intermix with each other. The intermixing of atomic orbitals is actually called hybridization process. So in this case, we have mixed in total 6 atomic orbitals, 1 from S, 3 from P and 2 from D. So we are going to have 6 new hybrid orbitals. We are going to have 6 new hybrid orbitals. Those hybrid orbitals will have equal energies, so they will also be regarded as degenerate orbitals, because all the new 6 hybrid orbitals are having equal energies. So I am making the 6 new hybrid orbitals. So these are the 6 new hybrid orbitals. Now, what will be the name of the hybrid orbitals? The hybrid orbitals has been formed by combination of 1s, 3p and 2d. So the name of hybrid orbital will be sp3d2 hybrid orbitals, and the hybridization is obviously sp3d2. So the second hybrid orbital will also named as sp3d2. Third one is also sp3d2. Fourth one is also sp3d2. Fifth one is also sp3d2, and sixth one is also sp3d2. So we are having 16.66% S character, 50% P character, and 33.32% D character per hybrid orbital. Now let's fill the electrons which are available in xenon in these sp3d2 hybrid orbitals. So in total, we are having 2 electrons in 5s, the total of 4 electrons in 5p and 2 electrons in 5d. So in total we are having 8 electrons. So we have to fill that 8 electrons in these new sp3d2 hybrid orbitals according to the Hund's rule. So that's the first electron, second, third, fourth, fifth, sixth. Now the pairing will start, seventh and the eighth. Now here, whenever any hybrid orbital is having 2 electrons or the pair of electrons, then that pair of electrons is regarded as lone pair of electron. I am repeating it again. Whenever a hybrid orbital has 2 electrons in it, then that pair of electrons is regarded as lone pair of electrons. So we got the first lone pair of electron in first sp3d2 hybrid orbital. Now let's come to the second sp3d2 hybrid orbital. Here also we are having 2 electrons, and these 2 electrons will be regarded as lone pair of electrons. Now after that, let's talk about the 4 fluorine atoms. Fluorine. What's the atomic number of fluorine? That's 9. So the configuration will be 2s2, 2p5. That's the valence electronic configuration. Now let's make the p orbital of fluorine. Now we are having 5 electrons in 2p. Let's fill that 5 electrons. First electron, second, third, fourth, and the fifth. So in 2p orbital of fluorine, we are left with one orbital which is having one electron, which is going to have head-on overlap with the sp3d2 hybrid orbital of xenon for the formation of sigma bond. So let's come over here. I'm marking the first fluorine, the 2p of first fluorine. That's the 2p of first fluorine atom. Now 2p is having 5 electrons, the first, the second, the third, fourth, and the fifth. Here one atomic orbital is left which is having 1 electron. So this atomic orbital of fluorine which is having 1 electron is going to have head-on overlap with the sp3d2 hybrid orbital of xenon for the formation of sigma bond. So we got the sigma bond, sigma sp3d2 p. As this sigma bond has been formed by head-on overlap of sp3d2 hybrid orbital of xenon with the p orbital of fluorine. Now let's talk about the second fluorine. That's the 2p of second fluorine atom. It's again having 5 electrons, the first, second, third, fourth, fifth. Here also we are left with one atomic orbital of 2p which is having 1 electron, and this is going to have head-on overlap with the sp3d2 hybrid orbital of xenon for the formation of sigma bond. So this sigma bond is again sigma sp3d2 p, as this has been formed by head-on overlap of sp3d2 hybrid orbital of xenon with the p orbital of second fluorine. Now let's talk about the p orbital of third fluorine. So that's the 2p of third fluorine atom. It's also having 5 electrons. So that's the first electron, second, third, fourth, fifth. Here also we are left with one atomic orbital which is having 1 electron, and this is going to have head-on overlap with the sp3d2 hybrid orbital of xenon for the formation of sigma bond. So we got the sigma bond, sigma sp3d2 p. Now let's talk about the fourth fluorine. That's the 2p of fourth fluorine which is having 5 electrons. Let's fill that. 1, 2, 3, 4, 5. Here also we are having one atomic orbital which is having 1 electron, and this is going to have head-on overlap with the sp3d2 hybrid orbital of xenon for the formation of sigma bond, and that's sigma sp3d2 p. Here all the sigma bonds are sigma sp3d2 p because all the sigma bonds have been formed by head-on overlap of sp3d2 hybrid orbital of xenon with the p orbitals of fluorine atoms. Now that's all about the hybridization. Now let's draw the structure of xeF4. So let's talk about xeF4. We got the hybridization to be sp3d2. The standard structure for sp3d2 is octahedral. Now let's make the structure. That's the xenon. According to the hybridization, we are having 2 lone pairs of electron and the 4 sigma bonds with fluorine atoms. So let's adjust all these in the structure. That's the first sigma bond with the first fluorine. That's the second sigma bond with the second fluorine. That's the third sigma bond with the third fluorine, and that's the fourth sigma bond with the fourth fluorine. Now I'm just imaginarily linking the fluorine atoms just to make you understand the structure in 3 dimensions. These are not the bonds. This is just a imaginary linkages. So we got the square plate of xeF4. We are left with 2 lone pairs. and we have to adjust that two lone pairs on the axial positions. I got the first lone pair on the first axial position, and opposite to this we got the second lone pair on the second axial position. Now, while naming the geometry of sp3d2 hybridization with two lone pairs, we have to ignore the lone pairs, and this geometry will be called as square planar, not the octahedral. So we got the name of geometry to be square planar in this case, because we don't have to consider the lone pair. Now let's mark the lone pairs in the Lewis structure. Here we are having the two lone pairs. That's the first lone pair of electron in one of the sp3d2 hybrid orbital. That's the second lone pair in the another sp3d2 hybrid orbital. Now, that's the geometry of xeF4. Now, at last, let's talk about the energy points. In the hybridization process, we are having two endothermic processes and one exothermic process. The first endothermic process, the process which is consuming energy, is the promotion of electrons from 5p to 5d. So I'm writing here is the consumption of promotional energy, that is energy required to promote the electrons from 5p to 5d. Another type of endothermic process here is intermixing of atomic orbitals. The intermixing of atomic orbitals requires energy. So at this point, here is the consumption of hybridization energy, as mixing of atomic orbitals is called hybridization. So at this point, here is the consumption of hybridization energy. Now, after that, we are having one exothermic process, and that exothermic process is the formation of 4 new sigma bonds between xenon and the 4 fluorine atoms. So I am writing energy is released when 4 new sigma bonds are formed between sp3d2 hybrid orbitals of xenon and 4 p orbitals of 4 fluorine atoms. And this energy released compensates the both endothermic processes, the promotional energy and the hybridization energy. From here I am writing which compensates promotional energy and hybridization energy. So both the endothermic processes are compensated during the formation of 4 new sigma bonds between the sp3d2 hybrid orbitals of xenon and the p orbitals of fluorine. That's why the formation of xeF4, xenon tetrafluoride, is chemically feasible process. So that's all for today. That's all about sp3d2 hybridization with 2 lone pairs, and the geometry will be named as square planar because we have to ignore the lone pairs while naming the geometry. So that's all. If any student wants to book a paid one-to-one online class to clear their doubts, then she can contact me. My phone number is mentioned on thumbnail of this lecture. Please do like, subscribe and share this channel to maximum number of students. Don't forget to press the subscribe button. Stay blessed.